and accordingly you will have chance to review it again, yes? And maybe someone didn't make it today, so he will also have. So we'll try to make these video records for every lecture. For practical exercises, we will have another room, so I will try to think of something else. But either way, I will try to provide some videos for you as well to catch up in case you miss anything, yes? So, okay, let us then begin today's lecture, and today we will have some brief introduction as to what exactly is machine learning, when we use that, how we can use that, what kind of algorithms are there, how are neural networks related to this, how do they work, and all that stuff. And then during the semester we will have much more detailed and somewhere also mathematical view on the certain aspects, on the certain algorithms, and we will also have, of course, a lot of practical exercises where you will have the opportunity to actually try and train your algorithm. We will even have the first problem next week, so that already next week you will have some algorithm trained from the data and see how it exactly works, what is the base for that, and so forth. So first of all, what kind of knowledge machine learning relies upon? So obviously we are dealing a lot with computers, and we rely heavily on computer science and the technologies themselves as well. That is hardware, that is software programming skills, etc. Yes, but also this is quite complex from mathematical point of view. So all these algorithms, all this training happens as mathematical functions. Yes, so in a sense you solve some mathematical problem, and that is actually training the algorithm to predict something or to classify something depending on the certain data that you have provided. We will use Python programming language for this. You can use Google Colab so that all your codes are always with you. You just need to log in your Google account on any computer and all your codes will be there. I will show that at our first practical exercise next week, so don't worry. But you can also easily use any standalone Python installation on any computer you have if it is faster, yes, so why not, yes. You have options. So the first question is somehow machine learning related to artificial intelligence? Is this the same stuff, or are there any differences between these terms? Well, artificial intelligence is somewhat more general stuff, and it is more related to the systems that are working, such as, for example, Google Translator. It is a system. It's artificial intelligence system that does translations for you. And the first experiments on trying to make machines somewhat intelligent were as early as 50s of the previous century, yes, after the World War, basically, and accordingly, of course, back then we did not have such computers, we did not have such technologies, we even didn't have such integrated circuits, what we could use back then, yes, so it was quite limited, but still some work was made, some progress was made, some systems were actually obtained that were working, something like self-driving cars and stuff like so, and of course it was limited to certain scenarios, like this self-driving car could only drive in a certain road section, yes, at a certain place, in certain weather. It couldn't drive at night, but it still was some progress, yes, back then. From that time, we have improved in our technology base and our knowledge and algorithms as well, so we can now speak about a subfield of artificial intelligence called machine learning. Now, machine learning mostly focuses on computer algorithms that are making this system able to predict something. So, in a sense, you can say that artificial intelligence systems are including algorithms to work, and specifically for these algorithms, machine learning is exactly the field of science that is studying it. So it's very tightly related to computer science, to programming and mathematics, yes. And then, accordingly, another smaller subfield in the machine learning is deep learning. that is relying on some algorithm, very specific algorithm type called neural networks, and particularly neural networks having a lot of layers. Yes, so it was inspired by nature. We took as example our brain, which has a lot of neurons, a lot of difficult interconnections between them, but of course even the most complex deep neural networks are still far away from our brain in their complexity, so it's just the beginning, we can say so. Still, they are useful, yes, they can do a lot of stuff for us, and we will also learn in this course as well different variants of these deep neural networks. But of course, first we'll start with the simple things, with a basic idea how you can train the algorithm to actually learn some data without having you to program the entire procedure. So what exactly is then machine learning is approach, or we can say also the science field, when you make some systems capable of learning from certain examples that you provide and making predictions based on their experience they had learned from that example you have provided. So in a sense, it is very similar as to how child learns to walk. Yes, it gets some experience and starts walking better and better. So algorithm is exactly so. The most important note here is that we mentioned that we do so without explicit instructions. What that means is that if you, for example, have to program some algorithm that will be able to say, is this a picture of cat or a picture of dog, then you don't need to necessarily program this entire decision-making procedure, like what makes the picture of cat, what makes this picture of dog. You might not even know this yourself. You entrust to figure it out for the algorithm itself. So you show some pictures to the algorithm, you say, this is a picture of cat, this is a picture of dog, please find what makes this picture unique, yes, in a sense, or what makes this picture to belong to this class. And accordingly, you don't have to program anything else. If you suddenly decide, okay, it works well with pictures of cats and dogs, now let's try pictures of bicycles and cars. Yes, so if you were programming that yourself, you would have to rewrite the entire program. This way, however, you won't have to change anything except that you will now provide different pictures as learning material, and it will relearn itself again. So we are here based on also, in a sense, probability theory, which we will study, yes, and statistical analysis, mathematical models, and of course, computer science, such as iterative algorithms. So most of these algorithms that learn cannot learn successfully from the first go. They have to repeat it over and over again. So it makes one iteration, it gets certain improvement, but it's still maybe having like 50-50 error rate. Then it repeats the process and continues improving, and by simply repeating this entire procedure, so meaning that it will go through all the pictures of cats and dogs again and again each time, improving until it meets the certain satisfying criteria, then we say, okay, it's enough, we can stop, or until it fails to get good results anyway, yes. So we are based on mathematics, probability theory, and algorithms. So in what kind of tasks can we use machine learning approach to solve our problems? Well, first of all, when you can't even define clearly how to solve this task yourself, such as this example with pictures of cats and dogs. You have no idea how to program computer to be able to predict if this is a cat or this is a dog by yourself. You don't know this formula, yes, to program. And even more so, even if you did, there is no guarantee that once you show some other pictures of other dog breeds or cat breeds, it will still work, yes? So again, how your hard-coded solution would work with the unfamiliar new data, yes? So that is also the question. Here, in this case, it should adapt automatically to that. Also, what's important is that you need to have certain examples of how it should work. So if we speak about trying to identify an object in a picture like a cat or dog, then you need to have pictures of cats and dogs in different environments, in different maybe lighting conditions in different breeds, colors, etc., etc. Yes, and also you also need to mark these pictures. Like you not only need to have just a picture of cat, but you also need to have picture and according label saying that this is cat. Yes, so this way algorithm will see picture, will know the correct answer, and will start calculating its so-called cost function. Yes. Another case is when you have some data and you want to find some pattern in that. So let's say like a few years ago, everybody was trying to predict Bitcoin change of the price, price of change of the Bitcoin. So they believed there should be some hidden pattern, so they tried to use these machine learning methods to figure it out in order to be able to say how much it might cost in future few days. Yes, of course, this is not always working because some events might happen which might not be considered by the algorithm or the data you have provided as input for this algorithm, because it's completely up to you to decide the factors that might affect Bitcoin price change. And if you have forgot some important factor, then the algorithm will only operate with what you have provided it with. Yes, so again, it's not as simple as it might seem at the first sight of the eye, that you have some data, you just load it to computer learns itself and gives you good results. No, you will still be responsible for getting this data, organizing this data, and cleaning this data as well of any unuseful information. And also, of course, if the volume of data is very large and you need, let's say, scan some pictures and read some, I don't know, postal indexes from this picture, and you have millions and millions of those pictures, then again, it's something we can entrust to computer and the machine learning algorithm to repeat these procedures, because the human would take a lot of time, much more time than the computer to work with this data. Considering, of course, you have these pictures ready. Yes. So, what exactly kinds of tasks we may solve by using machine learning methods? So, first type of task is called a regression task, and it's very close to some kind of regressions and interpolations we were speaking about in mathematics, or you will be speaking about in mathematics. Yes. That is the case when you have a lot of data points, like blue dots in this picture, and you want to try to find some certain pattern, a mathematical law behind this pattern, and to be able to predict, let's say, what is going to be the possible value if, let's say, we want to have x value of 100 somewhere here. We don't have this data yet, but seeing this pattern, we can, with certain probability, of course, predict at least a range in which it will happen. Yes. Similar, as I said, to Bitcoin prediction. Yes. So here we can see there is some sort of trend. Yes, as well over the years, and also some smaller fluctuations behind this trend. Yes. So this red line is this blue line without this logarithmical trend. Yes. So for that kind of task, we can use something called regression. And regression output is always any number it can be. Yes, from minus infinity to plus infinity with any accuracy that you want. Another type of tasks that we might use is called classification tasks, such as identifying objects shown in pictures, like this is a picture of dog or a picture of cat. In such case, the output is just a category number, like number 1 or number 2. It's not from minus infinity to plus infinity, it's just the limited, the discrete set of outcomes, yes? And in a sense, it is still very similar to the regression tasks. As you can see here, we have certain data points, yes? Well, at this point, it's not maybe exactly important what kind of problem it is, yes? It's not a picture identification example, it's, well, maybe something like some dimensions of certain parts at certain manufacturer point, yes, and this is the length, this is the width of the part, and accordingly here we try to separate which parts are faulty and which are good. So let's say green ones are good parts because their dimensions, their size does not, is not more than necessary, yes, and these are faulty parts. So in a sense here, as you can see, we construct a line just like in the previous example here, but now what we care about is, are we above this line or below this line? So from certain point of view, we can say that we still solve the regression problem. It's just that we change how we interpret our results, our output. So in case of normal regression task, the answer was ready and you could use it right away. In case of the classification, however, we will have certain probability that event has happened. So let's say we are trying to predict if this is a picture of dog, yes? So you will have as an answer some number in range from 0 to 1, depicting the probability that this is a picture of dog. So let's say 75% that this is a picture of dog. And then you have to decide yourself what is the threshold when you will say this is truly a dog. So is it 50%? So if we are about 50%, then it is dog, or maybe some other, depending on, of course, how many pictures you have of dogs and cats, because you might have more pictures of certain animal than other. Another type of tasks is clustering tasks, yes, when you actually don't know what you are categorizing. So consider here we have some basket of fruits where you have some apples, pears, strawberries, and what you want to do is to categorize them, put them in separate groups. So the group of apples, or the group of pears, and the group of strawberries, yes? In this case, it's very similar to classification, except that you do not have a mark at each apple saying that this is apple. The algorithm itself has to find similarities between objects and separate them into groups or clusters, and hence the name of this task group, clustering task, to accordingly make it. This can be used as a first step if you say have a lot of pictures of cats and dogs, just like millions of them, and you are too lazy to see each picture and write label dog or cat for every picture of them, or maybe this is just no time for that, yes? You might try to use clustering algorithm first, which will put all the pictures of dogs in one group and all the pictures of cats in another group. And then you will simply assign labels to all of them in one go. Of course, this will happen so that some pictures of cats might be misinterpreted as pictures of dogs. Some errors will still happen, but the majority of data should be still fine. And we also have the ways to check. By this method actually works different recommender systems. Like when you watch some video on YouTube, it recommends you some other content very similar to that, because it puts certain videos in categories by using different texts, etc., etc., yes? Just like any news portals, when you read some news about certain event, I don't know, maybe of some cultural activity, maybe about Olympiad, yes, then you have recommended other articles on similar topic. That is also work of this clustering algorithm. It puts similar articles for you to study as well. Now, another important point here is that some machine learning algorithms are requiring supervision from your side and some do not. So hence there are two large groups of algorithms. Supervised, when you have to provide correct answers, the labels to the solution, to the models which you want to train, and unsupervised, when you just have some pictures of cats and dogs and nothing about else, yes, no label, no nothing, and the algorithm has to figure out everything by completely itself, yes, and only then you can try to verify was it successful or not. So we'll be focused more on supervised methods, but many of the methods we'll be discussing can also be working in unsupervised mode, not necessarily like they have to be supervised. Yes, and we will of course also have some clustering problems to try out as well during our practical exercises. So what happens here is that you have a set of pictures with cats and dogs which you split in two parts. First one will be called a training data set. This training data set will be then given to the model to learn to predict the pictures of cats and pictures of dogs, and then accordingly, based on that, it will predict more or less successfully. Now, the idea then is to use this other part of data set which you have hidden away, the testing data set, which was not used during the training. So these pictures will be unfamiliar to the algorithm, yes? So the idea is not to test how well it predicts the pictures that you've given to him. The idea is to know how well it will predict new pictures in future, yes? So for this purpose, you have intentionally separated some portion of the pictures you had for later without showing to the algorithm during training to test it out, yes? And this is a validation process. Now, in unsupervised method, even if you have these labels, you may not to show them to the model. You may hide these labels for later to make the validation. If you do not have these labels, then of course there is no way for you to easily validate if it's working correctly or not until you have these labels, yes? Now there is one more type of the algorithm not shown here, yes? Sorry. Called reinforced learning. In the reinforced learning, basically you have a feedback. So in a sense, they work differently. They work like you are showing a picture of cat or dog to the child, let's say, yes, and if the child guesses correctly, then you praise him, give him some sweet, and say that he is a good boy. If the child guesses incorrectly, you say that you are wrong and give him nothing, yes? So in a sense, this is a similar approach in reinforced learning, like if the prediction is correct, the algorithm is, well, not praised with sweets, of course, but it gets a positive feedback, and if it's incorrect, then it increases some cost function, yes? So basically, as we will see, for algorithm, this replacement of the feeling, or how we can say, yes, is this cost function, and it tries to make the cost function as small as it can. So if it guesses correctly, then we do not penalize this cost function in any way. If it guesses incorrectly, then we add some big number to the cost function and it increases, so the algorithm understands that it's the wrong answer and tries to do it differently, some other approach, yes? So now also let's see artificial neural networks, yes? Here, of course, I can recommend you to check another course from Stanford University by one of the Stanford University professors who was doing this kind of courses and all that stuff. I don't remember how long ago, like 10, 15 years ago already. So he was like a pioneer in this sense, in actualizing these courses, yes. Now I believe this Coursera course might be somewhat different, but you can still search for it, yes, and try to use it if necessary. But also don't worry if you cannot find it. The course we will have here is more than enough, and I will try to give you as much materials as I can to pass it successfully, yes. So yes, maybe how exactly we will pass this course? Well, we will have a lot of practical exercises, like 9 or 10 of them, so your grade will be completely depending on these practical exercises. We will not have any kind of tests or exam even at the end, yes, because there will be just very much of these practical exercises. You do not have to do all of them, of course, you just have to do, let's say, 4 of them to get a positive grade. But the more you do, the better your grade will be, yes? And of course, these tasks will become harder and harder with each next pass. So this is considered by me a fair way to evaluate your results, and that's how we do so, yes? So, okay, let's, speaking about neural networks, let's start from beginning, yes? So, let's not dive into directly neural networks, trying to understand how exactly work, but let's start with something much more simpler, with much easier problem. Let's say you are owning a franchise of restaurants in different cities, and you have these statistics, like represented in this plot, where you have on x-axis number of people living in city in the tens of thousands, and on the y-axis you have what is your profit in that city in tens of thousands of dollars, yes? As you can see, some cities are even non-profitable, like here you have a negative profit, meaning that you are actually having some losses, but mostly mostly you have more or less profitable. And what you try to do is you want to try to find some mathematical function, the law, which describes how exactly your profit depends on the population. Of course, this is oversimplified problem, which does not include like any, I don't know, other factors like where exactly in the city is your restaurant, are there any competitive restaurants nearby, and all that stuff. Here we only make the very simple problem, like believe like we are the only restaurant in city, yes, and accordingly we try to figure out the profit. How exactly should we approach this kind of problem to find a precise mathematical solution, not like generic if I just take some, I don't know, pencil and try to draw the line and say, this is the pattern, yes? Well, this might be exact pattern or not so exact, so what we want to try is to find the absolute correct and precise solution. So this solution is a linear function represented by the formula theta 0 plus theta 1 multiplied by x. Here x is the variable, the population, and y is the output, yes, the profitability. Whereas theta 0 and theta 1 are certain currently unknown parameters. We don't know what exactly is this theta 0 and what exactly is this theta 1. And the task is to find the best theta 0 and the best theta 1 so that this line fits this data in the best way. Yes? So how should we approach this problem? Well, we could of course simply set computer to try brute force method, yes, like give array of possible theta zeros and possible theta ones, go through all of them, and then somehow to fix the best result. But again, there is no guarantee that you have initially basically hit the correct interval in which the best solution might be. So your best solution might be outside of the interval you have provided in your list of possible numbers, yes? So again, this is non-guaranteed method, and it also might be longer than necessary to find a solution. So here you can see some examples of possible lines, yes? And now what we need to decide is what exactly is this criteria that we are going to use to say that this fit is good and this fit is bad, yes? This criteria is called cost function, yes? Certain error, yes, of the prediction which needs to be minimal. And the smaller is this error of prediction, the smaller is this cost function. And in a sense, in this particular case, it will not be so in other cases, but in this particular case, this cost function is the mean squared error. Yes, you take the real answer, you take the prediction, now you subtract each of them, square it, because the difference can be both positive and negative. We don't want to compensate each other with plus and minus, yes, so we make it absolute value by squaring it, add everything together and divide by their number, yes. So in this sense, then you have the average error, how far is in general each of these crosses from this line. Now, as you can see, the best fit is the third one, the worst fit is the second one, and all of these have different values for theta 0 and theta 1. For example, this line, first line, has theta 0 equal to 5 and theta 1 equal to 0. And this is not a good match. Our task is now, based on this cost function, somehow to figure out how should we change this initial theta 0 and theta 1 to make it better. Now, for this, we use some method called gradient descent. Yes, I will not go into deep details today, but what I want to say is that having this error calculated will give you the lead as to where exactly you need to go. So consider we are right now at some point somewhere here, yes, you calculate the error of prediction, and this error of prediction tells you how much do you need to change theta 0 and theta 1 to end up somewhere here, yes? Then you eventually descend up to the minimum and end up here. So that is how exactly the gradient descent method works. We will program it ourselves, yes, even, so we'll speak of that later, yes, but in general, this is one of the optimization methods, and there are many, many other optimization methods. So eventually we'll start using some existing solutions, yes, but of course the first try has to be our own effort, our own discovery, in a sense, how exactly it happens. So the most important part is that now we can accordingly see that with each next iteration, like you repeat the learning process, in this case 50 times, yes, so 50 times you go over this data again and again and again, and with each next iteration your error of prediction is decreasing until certain plateau, yes, as you can see, not much effect can be seen after 25. So that means at this point we can safely say that more or less our algorithm has been successfully trained. Of course, future experiments might get a little bit more accuracy, but still, you know, it's a question, is it worth it to spend time on some very minor improvement or not? So this is how we then ultimately find out what it should be, theta 0 and theta 1, by using this gradient descent method, yes? Now we can consider somewhat more complicated examples when you have to predict outcome based on multiple factors, not just one of them, like population of city. So let's say you try to make a predictor of house prices depending on their size, total area, their age, the number of floors, the number of kitchens maybe, yes, and other stuff. It doesn't change much in this sense. You simply cannot plot it because now it has 4 dimensions, yes? 3 inputs and 1 output, so we cannot really display it visually. But you still can write this regression with multiple parameters. So now you will have theta 0 as before, theta 1 responsible for house area, theta 2 responsible for house age, theta 3 responsible for number of floors, and so on and so on. So now you have multi-parameters, and you still have to find them all. It happens exactly the same way, except that now you need to find not 2 parameters, but in this particular case 4 parameters. You still calculate the same cost function, you still apply the same gradient descent method, and it works. As we will see, we will write our program in such a way that even you will be able to simply change the data set, and the algorithm will work exactly the same as it was working with 1 column of data or 10 columns of data, yes? So that is our goal. And this can be represented, of course, in matrix form, and that means that actually in this particular case we don't even need machine learning to figure it out. We can solve this matrix set of equations completely mathematically to know the precise answer. And we'll try this as well. We'll compare it with machine learning methods, and the thing is just that we will need this to make sure that our method works correctly, because we will try to implement gradient descent ourselves, we will try to make the learning process ourselves, so we do everything with our own hands, so we need to have certain reference to know did we do correctly or not, and for this we can have this solution. Now, however, next problem will no longer have such exact solutions. So in this situation we cannot anymore have certain set of matrix equations and solve it completely precisely by using machine to calculate it, or pen and pencil to derive this answer. So in this case what we want to try to do is to have a classification problem called logistic regression. Now, the previous one was called linear regression because, well, you can see the function was more or less linear. Of course, we can also predict non-linear functions as well, but logistic regression goes beyond that. So let's consider another example of data that we have, like you try to basically enter some studies in certain university with very high requirements. You have 2 exams to pass before you are considered to be admitted or not, yes, and depending on your scores on these 2 exams, you are either admitted or not admitted, yes. So here you can see some statistics of students who had certain points in different 2 exams, so each exam was rated from 0 to 100 points, yes, and accordingly, as you can see, even if the student had this funny situation, having like getting maximum number of points in one exam and minimum number of points in another exam was not admitted, yes, and similar happens for the second exam. We need to find out certain line that is separating these two groups of data sets, yes, and this is going to be a logistic regression task. What we try to do is then to find this law so that you can say you enter in the window first score, you enter in the window second score, and it is going to predict will such students with such score would be admitted or not. So we try to make this predictor, yes, a classifier. In such case, our output is no longer a number in tens of thousands of dollars, yes, but just a plain number, 1 or 0, accepted or not accepted, yes. In linear regression, our range was from minus infinity to plus infinity. Well, in your particular problem, of course, it would be smaller. Like in this case, we can see we had like from minus $5,000 to plus $25,000, but well, it's just our particular case. It could be from minus infinity to plus infinity if we get more data. In this particular case, however, it's not a range, it's just a set of numbers, 1, 0, 2, 3, 4, etc., etc. Yes? So we need somehow to convert this result, because our function, which we try to display here, is going to have range from minus infinity to plus infinity. And we need to compress this range into range from minus 1 to plus 1. So here we add something called activation function. In this particular case, we add an activation function called a sigmoid, or logistic function, and hence the name of the logistic regression. So what is this function doing? So it takes your number, in this particular case z, and converts it into the range from 0 to 1. So minus infinity is 0, plus infinity is 1, and 0 is 0.5. And as you can see here already at minus 6, we can say that we are almost at 0, and plus 6 we are almost at 1. Yes? So this way we now convert this range from minus infinity to plus infinity into a probability. Yes? So 0 to 1 is exactly this probability that you will be accepted to the university. Yes? So we then do the following thing. We treat this problem exactly same way as we did before with linear regression. We still make this equation, yes, with theta 0 plus theta 1 x1 plus theta 2 x2, and stop here because we only have two inputs. Now this is going to be a linear problem, and we need to have a logistic output. So what we do is we apply this logistic function to our linear problem, combining them together. So as you can see, now we have this sigmoid of this linear problem. So normally we would find the solution as this straight line, yes, giving you some numeric values not in range from 0 to 1, but after you will make a sigmoid function here, it will be from 0 to 1, representing accordingly the probability of being admitted. As you can see here, this straight line is not the best solution because we have some incorrect points here, yes, like this should be above the line, whereas this should be below the line, yes. So there are some errors, but this is only because our line is too simple, it's straight line, yes. We could have had a more, well, higher order line with x squared, maybe x third degree, and accordingly, maybe it would be more precise. But we'll leave that for our practical exercises. We will have similar problems. The other important aspect here is that now our cost function is not a mean squared error, because your outcome is yes or no, basically. And you cannot say, like, it was almost yes or almost no. Yes, we are interested to know exactly if we make prediction correctly or not. So if it was yes and yes, then that is correct. If it was no and no, then it was correct. So this is a binary cross entropy cosine. It is now different, yes, as you can see, than it was there. Now, all this entire logistic regression problem can be represented as one single neuron. Yes, so you have your inputs x1 and x2. You have theta parameters, so here you have theta 0, here you have theta 1, and here you have theta 2 multiplied by these. And here you add them all together to get a linear regression, which you convert by this activation function into a logistic regression. Yes, so all this entire procedure can be represented as one neuron. And it's not difficult to see where I'm going, that we might take now multiple such neurons and make a neural network in the end. Yes, so that's exactly how it happens. Now let's consider a more complex problem where you need to classify not simply like yes or no, but to have more cases than that. For example, in one of our practical exercises, we will have the scans of the handwritten digits from 0 to 9, and the algorithm will need to tell what is the digit shown in this picture. Is it 0, is it 1, is it 2, and so on. So there are 10 possible classes, yes, and we cannot really use the algorithm that says yes or no to answer this kind of problem, yes. Don't worry, it's very simple. We are going to split this problem with 3 possible options into 3 different problems. Each of them can be represented as yes or no scenario. So in this particular case, as you can see, we have green triangles, red crosses, and blue squares as the possible outcomes of our output, yes? So what we are going to do is now to make 3 classifiers. The first classifier here is going to answer a very simple question. Is this a green triangle? Yes or no? And accordingly, that is the task for the first classifier. So we can say that we make a specialized classifier whose task is to search for green triangles. Similarly, we make the second classifier to search for blue squares, and the third classifier to search for red crosses. Each of them is going to give you the answer as a probability. Yes, so probability that this is green triangle, probability that this is blue square, and probability that this is red cross. So let's say here for some picture like this one here, we will have like here, we will have 0.75 probability for first classifier, 0.2 probability for second classifier, and 0.15 probability for the third classifier. So we pick simply the highest probability and say, okay, this is a green triangle. That's how this kind of problem works. And we can represent that in a form of neural network, not exactly like so, yes, but we will have now 3 of such neurons. They are not connected with each other yet, so this is not exactly a neural network because they are separate, but once we will start adding some hidden layer here, as example in neural network, we will have a neural network. So this is example of neural network which acts as a XOR element, yes, which makes the exclusive OR prediction. Exclusive OR truth table is shown here, yes, so if the inputs are the same, the output is 0. If the inputs are different, the output is 1, yes, and this neural network works exactly the same. The question here is now, how did I figure out that this has to be minus 10, this has to be 20, this has to be 20, this has to be 30, etc., etc. For that, I run the optimization procedure, and accordingly, the same gradient descent method, in fact, yes, which then found out this theta 0, theta 1, theta 2, theta 3, theta 4, etc., etc. And as you can see here, if we put inside of these formulas x1 equal to 1 and x2 equal to 0 and solve all of them, we get that the output should be 1, yes, which is true for this table. So the neural network in that case acts correctly, yes. As I said, these normally are unknown. You only start with saying, okay, I'm going to have this number of inputs, this number of outputs. I'm going to add in between here. Now this is something under your control, how many of such neurons you want to add, yes? So this is the number you set, like 10 or 20 or 1,000 or 2,000. as well as the number of layers. You can add one more layer of these neurons and one more. So this is completely up to you to decide, but then the algorithm will have to find the connections, the weight values, as to how important is exactly x1 for this particular node, and how important is x1 for this particular node, etc., etc. So you can think of these numbers as the important metrics, as the weights, as to how much input is affecting the total value, yes? And the solution is found by different optimization methods, such as gradient descent, for example, which we will program ourselves. But, well, here what we try to explain is how exactly this works, yes? So the training process of this entire neural network is actually quite simple and straightforward. You take all your data you have, so in this particular case, this entire table, yes, of 4 rows. Then you set some initial numbers, like you can't really set them to zeros because it will not work. Yes, you just have to put some random small values. So you pick them randomly and try to make predictions, yes, with this neural network that you have. It may not predict correctly, but then you use this cost function to calculate the error, yes? And based on this cost function, error calculation, yes, you change your theta parameters and repeat this process again. So if your optimization procedure works correctly, this time your error should be smaller, yes? And you repeat this step until the error change is, well, almost non-observable, yes? So at the top, in this picture, you can see how this error changes, yes? So this is some certain starting point where we start off, and with each next step, your error decreases, 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 until you hit this minimum, which might be long time necessary, and maybe you will decide to stop earlier than that, but it's still achievable. Now, how exactly it works and what role of derivative is in this entire process we'll speak about in our future lectures when we will discuss the gradient descent method. But right now this is just an introductory part, so we'll skip that part. And one more thing that I would like to add is that the sigmoid activation function is not the only possible way. Yes, you can use other kinds of activation functions depending on the certain tasks. If, for example, you are processing images, then certain activation function might be more common than necessary. If you have one class, then usually we use sigmoid activation function. If you have multi-class problem, then ReLU, rectified linear unit, might be better, etc., etc. Yes, so you can check them all in the Wikipedia easily, but as we go in our course, we will of course use them as well, and you will also have opportunity in practical exercises to test them, to compare them, how exactly it works with one activation function, how exactly it works with another activation function. And the outcome will be how accurately the algorithm will tell you what is shown in the picture, yes? So it will be quite obvious. So now, speaking of the neural network model, which we discussed already here, yes, we can specify multiple parameters. So first of all, how many layers do you want to have? This is completely up to you. You can use a lot, you can use less, and the problem is there are no clear guidelines as to in which case you should use how many layers. So in a sense, this is a certain research you have to do to start with some model, see how well it goes, and then decide, do you need to change anything in this model? Now, not all layers are exactly the same. We'll see that there will be certain specialized layers. Some layers might be better suited for image processing. Some layers might be better suited for text processing or speech processing, etc., etc. So there are different types of layers, which is also something to consider. Now, number of neurons in each layer is how big this layer is. How many neurons do you have? So here we have one hidden layer between and 3 neurons in this hidden layer. That's it, yes, but we could add more The question is it necessary? And what kind of activation function are you using at the end of each neuron? Well, normally, for this entire layer, we use the same activation function for each of the neurons. But, of course, if you make something very custom and very specialized, and you need to have, let's say, first two neurons having sigmoid, and the last neuron having, let's say, I don't know, rectified linear unit or tangent function, it is possible, but it's just that you will have to make such model yourself then. And the task is to find these numbers between connections of the layers for each of these neurons. So particularly in this situation, you can see we have 9 unknown variables which we need to solve for this neural network. So you have 2 inputs, you have 1 output, and 9 unknown parameters, yes? And you can imagine that growing this network will have much more of these unknown parameters requiring more time. So here you can see some example of deep neural network which has multiple hidden layers. In this picture they are shown in green color, yes, so blue color is input layer, red color is output layer, and green color is the hidden layers, yes, consisting of different numbers of neurons. And the connections between these neurons are shown with purple arrows, and each such connection has certain weight associated with it. So this is a certain number, like an amplifier in a sense, yes, that multiplies the input with it. Yes, and accordingly the goal is to find all the numbers for each of these arrows. Yes, as you imagine, if you have complex and deep neural network structure, there is a lot, like literally can be millions of these numbers that you have to solve. Well, not you, but the computer, of course. And as of such, you can imagine why training neural networks sometimes might take time. Yes, because you, first of all, might have a lot of data, which is in itself more data requires longer time, and the second, because you have to factor in all of these neurons. And when the neural network trains, it goes through each of these neurons in both directions. So that happens once in the feed-forward direction, so from input to output. Once it calculated the error, then it back-propagates that error in the opposite direction again, updating these weights, yes, but we'll speak of this in more details when we will discuss neural networks themselves. So don't worry if you don't understand something right now, because I clearly have multiple years teaching this subject and I know better, but for you it's just might be fresh impression, yes, so don't worry. The main thing that you need to understand that is that these neural networks might have a lot of neurons and hence a lot of time necessary to find the solution. Now, for deep neural networks, there are certain, we can say, variants, yes, specializing in certain tasks. Such of these examples, one of such examples is recurrent neural networks. So, in normal neural network, after it has been trained, the direction of the data flowing through it is just from input to output, just in one direction, yes? Now, in recurrent neural networks, the data is flowing in both directions. That means from input to output and from output to the input, yes? Why we might need to do that? Well, first of all, imagine that you want to, let's say you want to work with ChatGPT or make something similar like ChatGPT. Clearly, ChatGPT works with language, and in language words usually come in certain order. So the word now defines what it was the word before and what was the word after. Just like automated translation tools also have to put words in certain order. It's not enough for automated translator just to take every single word, to change language and paste them together, yes, because they need to rearrange these words depending on grammar of the target language, etc., yes. So words have to follow in certain order, and letters in the words also follow in certain order. So we need to consider the entire phrases, and that is where recurrent neural networks are actually excelling at. Yes, they work well with texts, and well, while ChatGPT is not exactly recurrent neural network, it is based on transformers, yes, so-called, but they have a lot of common with the recurrent neural networks as well. So you might even ask after this lecture on ChatGPT, was this exactly the algorithm you are running on and how it works? And it will answer you. I actually tried that. So what's important is that it considers the correlation between data. So that means if something is depending on what was before and what might be next, that is called correlation, and such neural networks work well in such conditions, which we will also study. Another example is something called convolutional neural network. Yes. Now, convolutional neural network has specific layers called convolutional layers, as you can see them here. Yes, with multiple stacks, we can say. And then, after all these convolutional layers, we can see our regular neural network, which we discussed so far, consisting of hidden layer and outputs. This particular problem identifies picture, what is written in this picture. So here we can see a digit 2. That means that this output neuron should have the maximum probability, and the other ones should have as small probability as possible. But in order to identify this number itself, well, not really in this particular problem, it's necessary to use convolutional neural network. You'll see that the regular neural network also actually works pretty well, yes, but the convolutional neural network will still work better, yes, especially if we try to identify not just digits like 1, 2, 3, etc., but some more complex objects like airplanes, cars, I don't know, traffic signs, yes, people, dogs, etc., etc., yes. So in that case, you really have to use the convolutional network. So what's important about the convolutional neural network is each of these channels, as you can see, is a certain filter that is set to search for specific patterns. Yes, like maybe if we speak in analogy for animal detection, like ears or nose or eyes, yes, so each of this filter is searching for certain part of the image, and together they put up the result, if it's 1, 2, or so, etc., etc., yes. So we'll speak of the neural networks and convolutional neural networks, of course, in the lecture. We'll have our practical exercise even on about this. It's just I wanted to point out that these are somewhat different networks, yes, which have additional layers and are well suited for data having the convolution to it, yes, such as images, yes, when you need to actually scan the picture with certain filter, that's exactly the convolution procedure, which is convolutional neural network excelling at. So, okay, that is what I wanted to show you for today. I will put this presentation, it has some more live examples as to how in my postdoctoral project, for example, I use different algorithms to analyze network traffic data, how I collected it, which you can study, you are more than welcome to. But for introduction part is what we have so far, yes? So are there any questions? Well, hopefully you will have more once we will go in more details, yes? And accordingly then, okay, so for today it's over. Thank you for attention. See you next week. One of the groups will have practical exercise in probability theory, yes? Next week. Thank you. And if you need to mark your presence here, I can do that also now.